with that, we'll start recording. So we're moving on to a new chapter today. Chapter 5 is about stereoisomerism, which is a topic we've talked a little bit about. We've talked about stereoisomers in substituted cycloalkanes, how disubstituted cycloalkanes can be cis or trans depending on where these substituents are attached. We also talked about stereoisomers in the context of alkenes, how alkenes can also be cis or trans, or even if cis and trans is broken, which sometimes it is, then we can use E or Z to distinguish between the two stereoisomers of an alkene. And that also falls under the general topic of stereoisomerism. But there's one more structural feature, and that's really what we've been doing so far, although we've already gotten into reactions a little bit. But a lot of what we've been doing so far is kind of setting the groundwork for organic chemistry. We need to set kind of the basis for future discussion, mostly in terms of structure of organic molecules. And there's one more kind of peculiar characteristic of structure of organic molecules that we have to cover before we go on. Up till now, I've kind of carefully avoided it, and so has your textbook. But it's something that we're going to have to cover, and that is the idea of individual carbon atoms in individual molecules. And then, of course, that molecule as a whole being asymmetrical, that is asymmetrical at the carbon atom. And another way of putting the same thing is to say that individual carbon atoms can be right or left-handed, just like people. Now, not all carbon atoms have the possibility of being right or left-handed, but some do. And I've made a little model over here that shows that. I think you can see that those two models that I've made are mirror images of one another. And those two mirror images, we're gonna, and I'll put the definitions up, of course, but those two mirror images, this might be CHClBrI or something like that. And that indeed is a molecule that can exist in left and right-handed forms, or we also call those two forms enantiomers. And I'll define that word as we get to it later in the lecture. But these two molecules are not only mirror images, they're also what we call non-superimposable, which is not a word we use every day, but it's also not particularly a scientific word. I could imagine it being used in other contexts. What I mean by non-superimposable is that no matter what we do, I can't superimpose this molecule on top of the other, meaning I can't place one molecule on top of the other such that all atoms fall on top of another atom of the exact same kind. I could, for instance, place the molecule, so the carbon, the hydrogen, and maybe we'll call the blue one the fluorine. I can place it so that those three atoms fall on top of one another, but now the chlorine and the bromine are backwards. You can see that. They don't match over here. I could place the molecules so the hydrogen, the carbon, and the chlorine and the bromine match with a little bit of work. Wait a minute. That was a lie. I can place it such that the hydrogen and I see what I'm doing wrong. I can place it such that the carbon and the bromine and the fluorine fall on top of one another. There we go. If we say the bromine is red, I guess that'd really be the bromine and the iodine. Anyway, I sort of think iodine should be purple because when you look at iodine solution, it's purple. I don't know. But in any case, those three atoms now fall on top of one another. Let me actually get it on the camera. But now the hydrogen and the fluorine don't fall on top of each other. And no matter what you do, there's no way to rotate these two molecules, since they are mirror images, such that they are superimposable. And that's a phenomenon that we run into sometimes in organic chemistry. And before we get a little further into that and maybe define some terms, I feel it's only right. I did a pretty terrible job at that, didn't I? I'm trying to show that they're mirror images. There we go. That works. So before we get a little more into that and get into defining terms and so forth, I do want to spend a little bit of time talking about why this matters. because I feel that my job is not only to tell you what you need to know, but I feel like I should at least make an attempt at telling you why it matters and why you should care about it. And, you know, maybe my reasons won't always be the best in the world, and I may not convince everyone with my reasons, but I feel I should at least try. I feel like that's part of my job, is to put all this in context. And so I at least want to try my best to do that for you. And I can think of two areas in which this idea shows up. Mostly, though, you'll find these things showing up in living systems, in sort of a biology or biochem context. One that comes to my mind has to do with our sense of smell. There's two molecules that are a little bit more complicated than those two, but that are enantiomers. They share the same relationship as these two molecules over here on the dot can. And they happen to be called plus carvone and minus carvone. You can also call them R carvone and S carvone, though I don't know whether the R is plus or minus in this case. But they are enantiomers. And we can normally distinguish them, though I'm told there's a certain mutation that it's possible you might have that you cannot distinguish the two. But most people can distinguish the two by their scent. One of them smells like spearmint and the other one smells like caraway seeds, which caraway seeds may be nice in your rye bread, but I think we'll all agree spearmint and caraway seeds smell quite different from one another. And that's directly because they are enantiomers. And I mean, I'll put this up in just a moment, but we're basically going to define enantiomers as being two molecules that are stereoisomers. We've already defined stereoisomers, and are also mirror images. Stereoisomers, you'll recall, a word we've already defined. Stereoisomers, that term applies to two or more molecules that have the same formula and the same connectivity. We already said, for instance, that constitutional isomers have the same formula and different connectivity. So stereoisomers have the same formula and the same connectivity, but a different arrangement of the atoms in three-dimensional space. And as I said, we've already covered some types of stereoisomers, cis and trans alkenes, for instance, or cis and trans disubstituted cycloalkanes. Those are also stereoisomers. And then I think it's very unfortunate that your book pretty much flat out says that conformations are stereoisomers when they are not. Conformations are different rotational states around single bonds for identical molecules. So identical molecules can never be isomers of any kind. So enantiomers are a special kind of stereoisomer. They are non-superimposable mirror images. And we'll also get into how you can tell when enantiomers or the possibility of this type of stereoisomers is coming down the pike. And then next class, I believe we have 2 classes. Yes, we even have 3 classes for chapter 5. That's great. That means I don't have to rush. Yeah, I think I might have done it again with that. I'd rather have too much time than not enough time. So I kind of thought we'd have 2 days for chapter 5. Be that as it may. But I want to go over how you can have a hint that this type of stereoisomerism is coming down the pike. So we'll get to that as well. But so that's one thing. Basically, enantiomers will have different properties. And the reason the 2 enantiomers of carvone smell different is because the receptors in our nose are 3-dimensional, like molecules are. And so they can distinguish between those 2 enantiomers. One has one smell, the other has a very different smell. And really, that's what this all gets down to, isn't it? It's that organic molecules are 3-dimensional. And lots of times, the 3-dimensional shape is not going to lead into this whole type of stereoisomerism, but sometimes it will. And so again, the place that usually shows up it involves biochemistry. So that's one, is the smell of plus and minus carvone, or R carvone and S carvone. Another area where this shows up is in the area of pharmaceuticals. And I'm not a pharmaceutical chemist, but this would apply just as much to pharmaceuticals taken by humans as to pharmaceuticals that we give to animals. So this is going to apply very broadly. And sometimes this type of stereoisomerism shows up. It means that it's possible for pharmaceutical molecules to have one or more of these chiral carbon atoms, like in this molecule over here. And that means you've got the possibility of left and right-handed forms. And this wasn't something that we appreciated until relatively recently. I don't think we really started to understand this until it was a little before my time. I would say the late 50s or early 60s. And it's kind of understandable because until then, a lot of the major drug molecules were not chiral, did not have this type of stereoisomerism. For example, aspirin has no asymmetric carbon atoms in it. And I'll even draw the structure of aspirin later, and you'll be able to see for yourself that this isn't an issue with aspirin. But it wasn't very long before we started developing molecules that had these left-handed and right-handed forms. And, you know, even though certainly by the 50s and 60s, long before then, we understood the issue of there being left and right-handed molecules, I think we just didn't appreciate how much it might matter. And one of the more dramatic examples, dramatic and tragic, has to do with a morning sickness drug called thalidomide that you might have heard of. This was developed in, I believe, the late 1950s. So again, even I'm not quite old enough to go back that far. But this particular drug had a chiral carbon atom in it. So it had left and right-handed forms, just like this molecule here does. And what people didn't realize as they were giving this drug to pregnant women and it was helping them, was that one of the left and right-handed forms was treating the symptoms of morning sickness, but the other one was causing horrible birth defects in the babies. And they didn't realize it, of course, until the babies were born. And so it was very sad. There's a generation at this point, they'd be about 10 years older than me, but so a lot of them I think will still be alive, of course. But there's a generation of, I don't know how many thousands of these thalidomide babies that have these birth defects. That they were not fatal in general, I think at least, but still very sad. And so, of course, as you can imagine, the drug was immediately pulled from the market. And nowadays, it's something that we're quite familiar with. To give a much less dramatic example, one over-the-counter drug that I think we all take from time to time is Advil. And Advil also has a chiral carbon atom in it. My understanding is that they don't bother separating the enantiomers, because one thing about separating the enantiomers is it's really, really expensive and really, really difficult. But in the case of Advil, I think, again, I'm no pharmaceutical chemist, but my understanding is that the two enantiomers interconvert in the stomach anyway. And so one of them, of course, helps with pain and fever. The other one is unpocotoxic to the liver. So that's why they place a pretty strict limit on how much Advil you should take every day, because over that starts building up toxicity in the liver because of the other enantiomer. I can think of also, and again, I'm not a medical doctor, I'm not a pharmaceutical chemist, but I know of at least one psych drug. If I really rack my brain, I'll remember what it's called. But there's at least one that you can get either in the pure enantiomeric form or in the mixture of enantiomers, and both are effective. And in this case, it looks like the quote wrong enantiomer doesn't have bad effects. But there's never any guarantee of that, of course. But just in this one case, it doesn't have any bad effects. So, but you can get the drug either way, and it depends how the doctor prescribes it. The doctor might prescribe that the patient take both of them, or might prescribe that they get the pure enantiomer, which of course will be much more expensive. So there's advantages and disadvantages. But the point being, this whole issue of chiral carbon atoms has direct effects on how molecules behave in the real world. It's something we have to be concerned about. And I mean, unless you're working in dispensing and packaging and making, the pharmaceuticals themselves. I don't know if it's something you'll have to work with constantly, but it's something worth being aware of, because nowadays, again, whether for humans or animals, it's not at all rare for pharmaceuticals to have chiral carbon atoms in there. So I think it's about time that I defined words like chiral. So let's do that first. Chiral carbon atom. I can set that up pretty easily for you. In order for an individual carbon atom to be chiral, two things must be true about it. It must first of all be sp3 hybridized. So there you go. And I'm not trying to browbeat you. There you go. Something from Gen Chem. You know, can't be avoided. It must be sp3 hybridized, and it must be attached to, whoa, what just happened? I didn't know I could write with my finger. It must be attached to 4 different carbon atoms. And I'll move that thing in just a moment. But not 4 different, sorry, 4 different groups. Oh, I didn't even notice it brought up the keyboard. So that's why it did that. There we go. Thanks. I didn't even notice the keyboard. So in order for an individual carbon atom to be chiral, both of those things must be true. It must be sp3 hybridized, and it must be attached to 4 different things. If either one of those 2 things is not true, game over. The carbon atom is not chiral. And we'll go over more about that in a moment. If for an entire compound to be chiral, in general, it's going to contain 1 or more chiral carbon atoms and be non-superimposable on its mirror image. Non-superimposable. Wait a minute, that doesn't look right. I'm sorry, I was raised to be a stickler about spelling. Is that right, or is it an I? I'll try it with an I and I'll see what it looks like. Non-superimposable. No, that looks like impossible. I think I was right to begin with. Non-superimposable. Yeah, I think that's right. Because again, here we go, uphill both ways. But when I grew up, of course, we didn't have spell checker. You know, we just didn't know how to spell things. And that was something that always drove me crazy, was ABLE and IBLE. But I think that's correct. Non-superimposable on its mirror image. Good. So the word chiral can apply either to individual carbon atoms or to a molecule as a whole. And so I would say this compound in my model over here is chiral because the one and only carbon atom that is in the molecule is also chiral. So that makes the molecule as a whole chiral. Good. So what else do I need to say about that? I think we also need to talk about enantiomers. I'm gonna sneeze. Enantiomers are a kind of stereoisomers. And I'll always write down what I say, but let me get it out of my mouth first. So enantiomers are stereoisomers of this type. They are non-superimposable on their mirror image, and they contain, or they are non-superimposable mirror images is really the best way to put it. Stereoisomers that are non-superimposable mirror images. Posable mirror images. Of this type, we call molecules like that enantiomers. So, and that's one type of stereoisomers that we're going to run into. There is another type that we're not going to talk about today. That will be more like either Wednesday or Friday. We get to these that are called Diastereomers. And those are simply stereoisomers that are not mirror images. Not that they're not superimposable on the mirror images, but that they aren't mirror images at all to begin with. And actually, this word diastereomers can be used to describe, for example, cis and trans alkenes. That's not wrong. You can call this cis-2-butene and trans-2-butene diastereomers. It seems a little weird and old-fashioned, but it's correct. You can use the term that way. We're going to talk about another type of diastereomers, though, also. And we'll find that they're a different animal from enantiomers. I'm trying to think if there's any other words I need to define up front. I can actually think of one. I don't know if we're going to need it, but it comes up in this context. And it's most of all in case I wind up using the word in class. I have often said, I don't know if you guys have ever played that game Taboo. Teaching chemistry is very much like teaching Taboo. For those of you who have not played the game, it consists of two teams, one of which is trying to get, there's like one person who gets a card with a word on it. And your goal is you need to make your teammates say that word. But along with that word, there's like, I don't know, half a dozen really, really closely related words. And so you sound like an idiot trying to talk around all these words. It's actually kind of fun, though. Even if you do look kind of like an idiot, but it's fun. Anyway, that's not all. Standing over your shoulder, looking at that same card with you, is some person with a buzzer. And that person is watching to see whether or not you say the word or one of those 6 or 8 closely related words. And if you do, they buzz you, and it's extremely irritating. So teaching chemistry is kind of like playing Taboo, and that I'll find myself using a word that I haven't defined yet. And I feel like the guy is over my shoulder with a buzzer, you know. So this way, I'll define the term in case I wind up using it so that person doesn't buzz me. Anyway, and the word is Racemic Mixture. I feel pretty certain we're going to wind up using this word or this term. And a racemic mixture is a special term used to describe a 50-50 mixture of enantiomers. Or 1-to-1 mixture, if you like. You can put it that way also. And the reason this term comes up is it's very, very common for a reaction to produce a racemic mixture as the product. That's really, really common. And like I said, it might be that we'll need that term. So just in case, just so the guy doesn't buzz me, we've defined the term racemic mixture. But I will say that and only that is the exact definition of racemic mixture. If it's 49-51, not a racemic mixture. If it's a 50-50 mixture of diastereomers rather than enantiomers, not a racemic mixture. It has to be an exactly 50-50 mixture of enantiomers and nothing else. So I think that's probably about all we need to define for now. Let me see, we're in 2:25. So what I want to do for our remaining 15 minutes is just going over some of these molecules over here. I'm going to start with this one here. I'm going to keep this in front of my, in front of me so that I draw it correctly. But let's see now. First, I have to just, let's decide for sure, at least for my sake, we'll say blue is fluorine, purple is iodine, and wait a minute. Oh, I was using chlorine. Okay, there's no chlorine here. So fluorine, iodine, bromine. Got it. That still works. So let's see. Hydrogen up here, bromine over here. This iodine is coming out at me. And I've got a fluorine going back into the plane of the screen or of your paper. So if we imagine setting up a mirror over here, then we can draw its mirror image or its enantiomer. And that's going to have iodine back here and fluorine back here. And if I did it right, that should be identically the same as this one. Let me see. Hydrogen up here, bromine over here. Yep, yes, indeed. I can see the iodines coming out at me, the fluorine's going back in. So indeed, those two molecules are enantiomers, which is just to say I did it right, which may not be a surprise, but I don't take anything for granted. So this is one way of drawing those two molecules. And so as a result, if we were naming them, we couldn't just call it, let me see, bromofluoroiodimethane. We need different names because those two are different compounds. So we need some way of distinguishing them. And that's where the RNS system comes in. So let me take this one first. What did we decide it was? This one must be the one. Yeah, this one is the one on the left. So let me see. This is fluorine, bromine, iodo. This is going. They're different compounds. Yes, they have different. Oh, I see. That's the problem. I need to prove to you that they're different compounds. The reason they're different compounds is because you can't superimpose them. They have a different structure. But it's a good question because one thing we find about enantiomers is they have identical physical properties except for one, which I don't want to spend a huge amount of time on since it's just not something I want to emphasize, but they do have, one way in which they have different properties is in living systems. So that's how you can tell they're different molecules. They might have different odors or might have different properties in terms of how they behave in living systems, because we have all these three-dimensional molecules like enzymes. Yes. Why wouldn't it be? Oh, remember resonance. With resonance, you're not allowed to move any atoms. Well, it's not just turned. They're mirror images of one another. I can't superimpose these things. Try as I might. I can get, these two atoms on top of one another, but then this part is mirror images. So these two will have different properties. Here I can get these three atoms on top of each other, but now those two don't match. So as a result, they will have different properties. And the one way in which they have different properties, I really don't want to spend a lot of time talking about optical activity. It's so old-fashioned and no one uses it anymore anyways. But there are instruments that you can put those two molecules in that will show different properties with how they interact with plane polarized light. Here we go. It's not a thing I really want to emphasize very much. My point only being you can distinguish those two molecules with an experiment. So that's going to turn out not to be true, by the way, with diastereomers. Diastereomers will have radically different properties, but we'll talk about that more Wednesday and Friday. So now I'm trying to remember, did I actually answer your question? Oh, good. I just wanted to make sure because, never know where my weird brain will go. So the point being, this is one way of illustrating those two molecules. And since they're different molecules, they need different names. We can't just call both of them bromofluoroiodimethane. We need a way of distinguishing them. And that's what I was in the middle of figuring out, which is going to be something I'll talk about briefly, not for a really huge long time. Let's see. The iodine's going to win. So we're going to go this way. That's a right turn. Good. So let me now put this back the way it was. Oh, wait, I first have to figure out what molecule that is. It's the one on the left? I'm sorry? Well, thank you for, it wasn't for sure that I was going to remember that. I think I put them down in the opposite place. This now is, wait a minute. Oh, I guess so. Yes, it is the one on the left. Now I forget, was it a right turn or a right turn? Okay. So the one on the left is a right turn. So this one we call R bromofluoroiodimethane. That's this one. And this one we will call S-bromofluoroiodomethane. And that's how we'll distinguish those two molecules. And that R and S system is sort of like the system of cis and trans or E and Z in alkenes. And actually, it's got a lot of similarities to assigning E and Z in alkenes. And one of the things I'm going to say is I'm not going to expect you to be able to look at a molecule and determine if it's R or S. Although the R and S system is very good because you can in fact do that. The other thing when I was answering your question about optical activity and putting an instrument, that way, that will also work, but you can't just look at the molecule. It's much nicer not to have to do an experiment, just to be able to look at the molecule. So I'm not going to ask you to be able to determine R and S, but I will expect you to know that the two terms are R and S and that they are opposites of one another. They're mirror images of each other. That I will expect you guys to know. So from these two names, we can see that those two molecules are enantiomers of one another. And I'll just let you know, if you can tell E alkenes from Z alkenes, you already in principle know how to tell R from S. I have left questions on R and S and enantiomers and diastereomers and meso compounds and all those great things. I've left all those in the OWL assignment because I want you guys to be exposed to the idea, and I don't think it will kill you to have to tell R from S once or twice. But in order to know what's going to be on the exam, as always, focus on what we cover in class. At least start there. And I don't think that's going to lead you astray. And I will often do that. I will often leave things in OWL assignments, even if it's something I specifically say you don't have to know for the exam, just so you can kind of see how it's done. But I will always be clear in the class notes and clear in the syllabus about what is fair game for the exams. And at this point also, you've had one of my exams, now you know what to expect. So, so the reason I'm not making you learn how to tell R from S, which I just kind of did like 3 or 4 times, because I couldn't remember what I had come up with. The reason is mainly because it's a real pain in the butt. It's a long process to go through. See, to tell an E alkene from a Z alkene, all you have to do is look at pairs of carbons. You look at this carbon and the 2 things that are attached. Great. Then you look at this carbon and the 2 things that are attached, and then you're done. It's much easier. With these, you have to look at 4 groups, and you have to decide how they all relate to one another. It's a pain. It's a long, drawn-out process to come up with an answer RS when literally you could have flipped a coin and had a 50% chance of coming up with the right answer. So I don't think it's worth your time. It's an awful lot of work for very little payback. I left it in the OWL assignment, as I said, so you can see how it's done. I don't see anything wrong with that. But I'm not going to say, anyway, wouldn't that be kind of a stupid question? Here's a compound, what is it? ARBS. It's kind of a dumb question. There's only 2 answers. So I just don't think it's worth it. But I will expect you to know that the 2 labels are called R and S, and that they refer to enantiomers. That is, if you have a compound that's in the S configuration, then its enantiomer will be in the R configuration. Starting next time, we're going to start to consider what happens when there are multiple carbon atoms. That's when things start to get interesting. But I think that I do want to do just one more example of this type of molecule. And then I think we can start talking about multiple chiral carbons. We can save that for Wednesday or Friday. Good. Any other questions about the R and S labels then? Sure. I kind of see what you're, well, let me see if this answers your question. And if not, we can do a follow-up. I believe the answer to your question is no. This way of assigning absolute configurations is always going to work out a certain way. So if one of them is R, it's for sure R and will never be S. And then the enantiomer will for sure be S. So do you mean like, could there be 2 R's? No. Mm-hmm. Does it matter which one? Oh, absolutely. One of them will, yeah, one of them will absolutely be S and one of them will absolutely be R. And there's ways of doing that. I just don't think it's worth the trouble.
I was just curious.
Yeah, no, and that's fine. Now I'll tell you where, I'll tell you where this does matter. Do you remember when I talked about plus and minus carbon? That's the old way of distinguishing between enantiomers is plus and minus. That you can't tell just by looking at the molecule. See, and there's also no relationship between RS and plus minus. So the R enantiomer might be plus and it might be minus. And there's no way of knowing without doing an experiment. So that old way, we don't use that anymore. This other way is much more convenient. But yes, I just don't see the point of your guys going through all this effort when you could literally flip a coin and have a 50% chance of being right. It's just not worth your time. That's what I think. Good. Well, we have 3 minutes. I really wanted to do one more. Let me at least set it up. And if we have to continue it next time, that's fine. See, we avoided the issue beforehand. We would talk about a molecule like 2-chlorobutane. But as it turns out, 2-chlorobutane is a chiral carbon. That carbon is chiral. It's attached to hydrogen, chlorine, methyl, and ethyl. So 4 different groups. So that carbon is chiral. And that means now, if we're just talking about the molecule in general, and we're talking about something where it doesn't matter that the carbon atom is chiral, then we can just draw a flat structure like that, and it's perfectly fine. But in fact, there are 2 enantiomers. One will look like this. And the other, that's an H, although you'd be hard-pressed to know it. And the other, this is another way of doing it. We would have the hydrogen in front and the chlorine in back. So those 2 are different molecules. They're mirror images of each other. And I could make a model. And in fact, next time I very well might make a model to show you guys this. So now the only thing that's left is for me, since I wouldn't ask you to know how to do this, let me figure out which one's R and which one is S. I'm going to do it on this one since it's easier. The chlorine's going to win, then the ethyl, then the methyl. We're going this way. I call that a right turn of my steering wheel. So this one is R and this one is S. So what I just did there is what I'm not expecting you guys to know how to do. But I would expect you to know that surely one is R and one is S. And they're going to be enantiomers. They're going to be mirror images of each other. So this is another example of 2 molecules that are enantiomers. And actually with that, I'm basically out of time, though I might start with this example next time. I like having the extra time this term that we took some chapters out. Good. So have a great day. And shouldn't have turned it off just then, but I'll see you all on Wednesday.